Hello ladies and gentlemen, and welcome back to lecture 11 for GGS 300, Quantitative Methods for Spatial Science. Today we're going to be focusing on categorical difference tests, and you are probably aware now that we're in the run-up to the next midterm, which is going to be due on November the 11th, and I've already put that up on Blackboard, as well as the ungraded preparatory tests that I've put up there for you to kind of get a kind of grip for the kind of content you're going to be tested on, okay? So don't hesitate to reach out to me if you've got any queries on any of that. You'll have to basically complete all of those ungraded tests and then the final midterm before November the 11th. So today is going to be a relatively short lecture, and I'm just going to go over 3 different approaches to testing categorical differences within data. So you should be very aware now that we've moved on to this more formalized part of the course, and we're running up into the end of the second third before that second midterm. So basically from next week onwards, we're going to be into the final third of the class. And this week we're going to be focusing on this part of the flowchart, so specifically the kind of discrete and categorical data component, focusing on things such as the chi-squared test. So really what we're doing here is we're actually testing the goodness of fit of certain data outcomes that you may empirically collect. So you go out and you carry out a survey and you get a bunch of questionnaire data, okay? And those questionnaire data responses are going to be non-numerical information. They're not even going to be ordinal, so there's no kind of explicit order within things like gender preferences, or maybe you get responses for certain variables and they're broken down by different socioeconomic factors. It may be also included race, for example, and therefore there's no way for you to kind of use numerical information, numerical tests like we have done in the previous case to kind of test the outcomes for these. So you may be wanting to use some other types of essentially non-parametric, in this case, categorical tests. So I know that you're probably going to be like, oh no, Ed's making me learn even more tests, and we've already learned far too many. So what we've basically covered is one sample test, so comparing the mean sample statistic to a corresponding population parameter. Comparing 2 different samples, so evaluating independent samples to see whether they're significantly different from each other, or evaluating 2 different samples which have been collected from the same sample entities. Okay, this is where we did the matched pairs tests. Or more recently, what we focused on are those 3 or more sample tests, where essentially we've been covering analysis of variance and attempting to estimate whether at least one of those samples has come from more than one different population. Okay, so nominal data, as I just explained, we have problems with this. We can't use these existing tests, so we need to evaluate the goodness of fit. That's the way that these are basically evaluated. And today we're going to focus on the chi-squared approach, the Kolmogorov-Smirnov goodness of fit test, and the more easily calculated Shapiro-Wilks test. So these evaluate whether data are normally distributed or not, and then we'll be focusing finally on contingency analysis. So I'll go more into those at a later date. But essentially we're using the chi-squared distribution for the first case and the third case, so the chi-squared goodness of fit test and contingency analysis. But in the Kolmogorov-Smirnov test, we're focusing on whether ordinal data actually fits an expected frequency distribution. Okay, so we're comparing an observed frequency distribution to an expected one. We're asking, well, how much does the distribution deviate from what is expected? So can we, with 95% certainty, conclude that the results haven't just occurred by chance, that this deviation is greater than we would just expect if we just randomly sampled from a population? And this deviation can be in terms of whether the data are distributed in a uniform way, whether they're distributed based on some sort of proportional distribution, or whether they're actually normally distributed. Okay, so if they're uniformly distributed and they're proportionally distributed, we'll use the chi-squared statistic, and if they're normally distributed, we'll use the Kolmogorov-Smirnov approach, which is slightly different. So for the chi-squared goodness of fit test, basically what we're doing here is we're comparing observed frequencies with the expected frequencies, and there are quite a few requirements. So we would expect that the sample that we're collecting, just the single sample, is randomly collected, that the data that we're collecting is basically a nominal or ordinal with frequency counts, and there's no expected frequency in there less than 2, and no more than 1/5 of the expected frequency counts are less than 5. Otherwise, we may break the requirements for this test and produce unreliable results, essentially. So our null hypothesis is that the population actually fits this expected frequency distribution, and the alternative hypothesis is basically that it doesn't fit. And basically we're evaluating here based on this chi-squared test statistic. So to get the chi-squared, what we need is the number of nominal or ordinal categories k multiplied by, and then what we're going to do is we're going to subtract the expected frequency count from the observed frequency count, square it as the numerator, divide by this EI again, and that gives us our chi-squared statistic. Okay, so if all the observed values are close to the expected, and the differences would be very small, and as a consequence the chi-squared would be small, and therefore we would fail to reject the null hypothesis in that particular case. But if we have at least one observed value that's very large, the chi-squared will be consequently large, and then it would mean that we would, with most certainty, reject with most likelihood, we would reject the null hypothesis at that point, okay? Probably because we get a p-value that would be below that 0.05 significance level in order for us to be 95% certain that the results haven't just occurred by chance. So if you look in the book at page 189 in McGrew, we have an example. So we've got random samples from 5 different schools of 100 students. And basically what we want to do is we want to actually assess whether the distribution for the schools is above the national median. Sorry, we want to assess whether the distribution of above national median scores is uniform between the schools. Okay, so we're looking at whether any of the schools are basically different from the national median. The observed number of students is here. So for Muir, this school has 42. For Pinchot, 45. Carson, 51. Hardin, 47. Leopold, 60. So basically, we want to get this chi-squared value, and then we need to work out this EI value, so the expected count first. So basically, to get the EI, we need to take the sum of the observed values here, which is 42 plus 45 plus 51 plus 47 plus 60, which gives us 245. And then we need to divide it by the number of groups that we've got, and we've got 5 schools here, so we need to divide by 5, and that gives us our value 49. So then basically what we can do is we can plug that EI value in to each one of these schools. So we'll start with Muir, so we need to subtract this EI, expected value, from the OI, so 49 minus 42. Sorry, 42 minus 49 squared, and then divide by that 49 expected outcome again. And then we can do that for each one of these schools. So you'll see that Pinchot, the 45 observed, goes in here, and the 51 observed in Carson goes here, the 47 observed in Hardin goes here, and the Leopold 60 observed goes here. And then when we basically crunch these numbers together, we get a chi-squared of 2.007. With 4 degrees of freedom, that's a p-value of 0.734, so that's nowhere near the 0.05 significance level that we would expect when we want to be 95% certain that we actually have something that deviates from the null. So as a consequence, here we're actually failing to reject the null hypothesis, and we maintain the null as the existing status quo, that basically none of these schools here actually deviate from the national median score, okay? So that was the first test. On the second test, what we're doing here is we're focusing on the Kolmogorov-Smirnov approach. So we're using ordinal data to judge if the distribution fits some frequency distribution, such as the Gaussian normal distribution, okay? So if the data set actually resembles the normally distributed data. So it's kind of handy if you want to basically test, and I've used this a few times in my own work, if you want to test to see whether your data actually fit that normality assumption. So maybe after this, you'll go off and you'll do research, and in that research you might do a dissertation, and you'll produce a set of maybe statistical assessments, and you'll want to check whether they are parametric, and as a consequence you might carry this out prior to fitting the models based on the parametric approach to basically show that the data that you've got are normally distributed. This would be a good way in order for you to make that decision rather than just kind of qualitatively looking at the distribution of the data. So what we do is we use the cumulative relative frequencies in this approach. So we compare sample data to a perfect normal distribution to see if they match. So if we've carried out the Kolmogorov-Smirnov test and the distribution is not significantly different, so we retain the null hypothesis and the status quo, we would opt for a parametric test for our data. If the distribution is significantly different, however, so we're basically rejecting the null hypothesis and accepting the alternative hypothesis, after carrying out this test, then we would basically opt for a non-parametric test, okay? So this is a kind of ordinary histogram, and this is the cumulative histogram that we would use in this approach. And I'm not doing it this week, but I think in our first laboratory session, when we in a week's time, I think we do carry out a few of these tests, so it kind of brings you up to speed with what you need to know in the lab. Obviously this week you've got your tests to revise for, okay, so I'm not going to overload you with work while you're doing that. But essentially this objective is to see whether a random frequency count sample is basically fitting along with an expected count, okay? So we expect that this is randomly sampled data and the population is continually distributed and the variable is ordinal. So you might have to downgrade from interval ratio data into ordinal. But basically the null hypothesis would be that the sample is the same as the expected count, so there's no difference there, whereas the alternative difference, the alternative hypothesis would be that there's a significant difference from the expected frequency count, and therefore, for example, it would demonstrate that the data don't conform to those normal Gaussian distribution assumptions. Here we're using the test statistic D, which is basically the maximum absolute difference between the observed and expected cumulative relative frequencies. And it's more tricky to kind of carry this out by hand, so we're not going to do that. But basically we're going to take the maximum of the cumulative relative frequencies for observed values of x minus the cumulative relative frequencies for the expected values of x, okay? So KS, the Kolmogorov-Smirnov test, is difficult to do via manual calculations. Okay, so you need to convert the actual rank data to z-scores, calculate the cumulative normal values and cumulative relative frequencies, compare with the cumulative relative frequencies, and then make a comparison with, the cumulative relative frequencies against the normal distribution. So essentially, we're not going to be doing that in this test, but what you would normally look out for is that the maximum absolute difference between the observed frequencies and the expected, you would compare the maximum absolute difference between the observed and the expected. Okay, so if the difference is small, we'd have a small d. If it's large, we'd have a large d. And then you can do this either in R, as we'll do later, or you can use something that's easier to calculate, which is basically called the Shapiro-Wilks test. So basically, we'll be running this at a later stage, and essentially this just tests for normality of the data. So you can use this R function, Shapiro.test, curly brackets. So in this, we're basically just assuming that the null is the distribution is not different from the normal, and the alternative is that the distribution is different from the normal. And there's some specific tests, some specific differences that you need to be aware of when using this approach, okay? So normally, we would expect a large test statistic to lead to a significantly different result. That's somewhat different here. We would expect a small W statistic, so it's basically the opposite, to indicate that we would reject the null hypothesis, okay? So this is kind of different. We're also not looking explicitly to reject the null hypothesis in this approach, okay? And there are also some sample biasing issues. So I don't want to get too bogged down in that. We'll also pick up how we do some of those calculations at a later stage in the laboratory session. But just to finalize today, essentially this contingency analysis, we have two categorical variables, okay? What happens if we want to actually cross-tabulate the frequencies across those variables? So before we were comparing an actual observed frequency distribution against what we would expect to occur, so some sort of expected frequency distribution. So rather than comparing our actual observed frequencies against the theoretically expected outcome, we're basically comparing the distributions of two empirically observed variables, okay? So the aim is to see if they're different, independent, or related, so not independent. So this is an extension of the type of goodness of fit approach we covered earlier. And it evaluates the whole contingency table as a single entity. And I'll explain what I mean by a contingency table, but this is basically a table showing cross-tabulated frequencies of counts over two different variables, okay? So I'll explain what that means in the next slide or so. So you can think of a contingency table as a cross-tabulation, which is probably closest to how you might want to think about this. You could also call it a confusion matrix or an error matrix if you were doing some sort of more fancy statistical learning-based approach, as is kind of common within the machine learning and AI field right now. Really, the way that I kind of think about this is that, you know, you have this variable x here with these two different binomial outcomes, so either 1 or 0. Let's just think of this as either true or false. And then basically you have a variable y over here on the y-axis with the same outcomes. And then basically here you would get a number for the number of times that you had both a 0 and a 1 occurring at the same instance, okay? So that would fill this individual part of the matrix, and you would get the same down here for those cases where you would have the number of outcomes which had a 0 for x and a 0 for y, and so on and so forth across here. So there used to be a piece of statistical software called Minitab that I used when I was doing my undergraduate degree, and you know, that was kind of a specialist piece of software which focused on partially these types of cross-tabulation statistical approaches. So you have to do a little bit of number crunching in order to get that chi-squared test statistic, but basically we're comparing the observed frequency counts for independence for two different empirically collected variables. So we need randomly collected data from a single sample. We need variables that are nominal or ordinal with the frequency counts for each of those. And then finally, we also have to make sure that none of those expected frequencies are less than 2, and that we have no more than a fifth of the expected counts being less than 5. Okay, so in the null hypothesis case here, what we're basically saying is that the variables are statistically independent, so there's no relationship between them. Whereas in the alternative hypothesis, basically this is where variables are not statistically independent. So the chi-squared value here is what we want to obtain, and to get that we need to take the total number of rows multiplied by the total number of columns multiplied by, and then we're going to subtract this EI, the expected frequency count for the rows in the column, for a particular row and particular column, from the observed frequency count for a particular row and particular column, square it as the numerator, and then divide by this EIJ again, this expected frequency count. So the trick to get the expected frequency count is that we need to take the sum of all the observed frequency counts in row I and multiply it by the sum of all observed frequency counts in column J, and then divide by the total number of observations. So let's just go through one particular example. I'm giving you it here based on just a little hypothetical case. So let's assume that we go out and we poll GGS quantitative methods students, and we ask how much they like quant courses. So I can imagine before we begin that we might get a few negative responses to this, because, you know, some people don't like particularly statistically based classes. But essentially what we get is, for each of these majors, BA in geography, BS in geography, or other, we get these responses. So either you like them a lot, either it's okay, or either you don't like it at all, really not at all, you kind of detest them. And then essentially what we've got here are the row totals. So this 15 represents the sum for all BA geography, 20 for all BS geography. These are for the people who have been surveyed. And then we've got the others as well. And we've also got the column totals here for the different responses. So 17 across for a lot, 19 for it's okay, and 14 for not at all. And then basically we can get the expected frequencies here. So to get the expected frequency, this EIJ, we need to multiply the frequency count for the row by the observed frequency count for column J. So we've got 15 here for this first BA geography row, and that's the column total, so the row total. We've got 17 down here for the column total. So what we're able to do is go the row multiplied by the column. So that's 17 multiplied by 15 divided by n being 50, and you should end up getting this 5.1 expected frequency count, okay? And then basically you can get those for the rest of the different cells here. And then finally what we're able to do is we're able to pin those numbers into here. So this is the e minus o squared divided by e, and we get these different numbers here. So to get this value 0.708, you would basically subtract the expected value of 5.1 from the observed value of 7, square it, and then divide it by 5.1 again, and that should give you this 0.708. And then basically we can sum all of those values. Here we go. And it gives you 2.763. And then basically we can test the p-value for that, knowing the number of degrees of freedom. And here we've got a number of degrees of freedom of 4. And basically the p-value you get is 0.598. So that's nowhere near the 0.05 significance level that we would expect if we want to be 95% certain that the results didn't just occur by chance. So in this particular instance, we would fail to reject the null hypothesis. Okay, well that's going to conclude the second part of the course, and that means that the upcoming midterm exam will basically cover all of the stuff that we've been over the past, I think it's 5 or 6 weeks, okay, so the middle chunk of the course. I think that maybe this was a harder part of the course relative to the first chunk, particularly as you kind of had to cement some of those ideas of probability that we covered in the first part of the course, and basically take them a bit further in the second part by formally testing these hypotheses. But I do think that now you're into the realm of really kind of rewarding statistics, because you can go away and you can apply these statistical approaches to any types of phenomena that you wish to actually study. So I think that that's a really powerful set of kind of skills and tools that you've got at your disposal. So I'm not going to take too much more of your time. Do make sure you go over the ungraded tests, and don't hesitate to reach out to me if you've got any further questions prior to the midterm. Otherwise, it should now all be on the Blackboard website, and you can basically just do that at your leisure. Just make sure that they're completed before that November the 11th deadline, as that's when the grading will close for that part of the exam. And obviously if you submit your grades later than that, then that's going to be a problem. You're going to lose a certain number of marks depending on how late it is. Great, so have a nice day. Thanks for tuning in, and I'll catch you all soon. Goodbye.